Now, backward propagation. The learning is to update the weight, as you know, weight of the neural networks, to minimize the objective function and by a gradient descent method. So about this gradient descent method, we're going to talk about it in the numerical optimization chapter, in the next chapter. Okay? And the backward propagation from the loss function to the first layer. So this propagation goes from the output to input. Okay, so from the forward propagation, we got the estimation. Now we want to compare this estimation to the target label. And then we can define the loss function. Maybe a simple example of loss function is just the difference. So we want to minimize the difference between this estimation and the target label. Okay, that would be one good example. And then we have an error here. When we take a derivative of this loss function with respect to these parameters, then this derivative can be represented as a chain rule. And once we have this derivative, then we can update the parameters based on this gradient information. So the idea is quite simple. Apply the forward propagation and then define the loss function and then take a derivative with all the parameters and then update the parameter based on the gradient information. So in training, and there is a credit assignment problem. So the credit assignment problem says we need to figure out how much contribution each node is making to the error. So how much do we have to update a specific parameter? This derivative does that. Okay, so let's see the equation in detail. We assume that we have a C classes with L layers. So in this figure, we have a 2 class, which means we have 2 output nodes, and then we have 3 layers. Okay, so in this graph, we have input layer and first layer and second layer and the third layer. So it looks like we have 4 layers, but you can just focus on these layers, 2, 3. And we have input X, and after applying this matrix, then now we have A. A is right before applying the nonlinear function, and the B is right after applying the nonlinear function. And then we apply the matrix multiplication to this B, and then we get this A2 and apply the nonlinear function. Now we have a B2. Then apply the matrix multiplication, then we get AK, and apply nonlinear function like a softmax, then now we have YK. This is for the propagation. And if we use the equation for that, then it looks like this. So from input, let's go from the bottom, and we have input X. Then we can multiply this matrix to get this one, and apply the nonlinear function to get the B1. And the first layer is different from other layers, and the last layer is different from other layers. But in the middle of this, then all the layers have the same kind of formula. Let's say we have a BL, then we multiply this matrix, then now we have AL plus 1, and we apply nonlinear function, now we have BL plus 1. And in the last layer, we multiply the matrix, then we get AK. And we can apply sigmoid function for 2-class problem, or if it is multiple classes, then we have softmax for classification. For regression, sometimes we don't need these functions. Just the AK would be enough. Or if you want, you can come up with your own nonlinear function, but we don't have to have a sigmoid function or softmax. These two functions are only for classification problems. But anyway, for the propagation, these are the all equations we have. From input, multiply the matrix, and then we got the A, and apply the nonlinear function, we got the B, and iteratively we run these layers, and this equation can be rewritten by a matrix formula. So this is vector, and this is matrix, and this is vector. So in these equations, we have element-wise equation. So basically these two equations are the same. Okay, so for the propagation is not that complicated. In neural networks, the subscript and the superscript might be confusing, but the equation itself is not that complicated. Just the matrix multiplied by the vector and the addition and applying the non-negative function. That's it. Okay, now we'll talk about objective functions before talking about backpropagation, because we need objective function. And then we can think of maximum likelihood estimations. So we already talked about these maximum likelihood estimations and the density estimations. So we don't have to go through all the details, but let me repeat this thing one more time. The basic idea of this maximum likelihood is simple. The question is, which distribution explains the data better? So when we have data samples here, then which distribution? So we have this one and this one, this one. In this slide, it looks like we have only 3 options, but these parameters can be continuous. So by moving these parameters, we can have infinitely many distributions. Then how can we find the best distribution? We can define the likelihood equation, then we can take a derivative. That's it. So anyway, the basic idea is quite simple. Under which distribution are the samples more likely? If the samples are around here, then this distribution would be better. And if we move the data samples like this, then we have to update these parameters so that the distribution should look like this. Okay, so now in the previous slide, for the propagation, we had output as a probability based on the sigmoid or softmax. So now let's assume that we have probability. Then let's think of likelihood for a single input and target label. So we have only one sample, input and the label. And if it is a 2-class problem, then this is likelihood. Okay. So the probability of t given x is like this. And the y is the output of the neural network. Look at these equations. Then when t is 1, this is binary classification. Then when t is 1, then this probability is just y. Okay. If t is 0, then probability is 1 minus y. Okay, so which means when the neural network's output is y, let's say this one is 0.3, then what is the probability of class 1? It says it is 0.3. Then what is the probability of class 2? That is 0.7. Okay, so we have only one output value, and with this output value, then we can classify. And if it is multiple classes, then we can have these equations. If you are confused, then you can think of just a simple example. Let's say when t looks like this, which means the target label is the 3rd class. Then the neural network has the 3 outputs, y1, y2, and y3. So let's say this one is 0.1 and 0.2 and 0.7. And then what is the probability? T looks like this, which means the true label says it is the 3rd class. Then what is the probability? Look at this equation. When we have 3 classes, it looks like y1 t1 times y2 t2 times y3 t3. And we assume that the label is the 3rd class. So first one is the 0, and second is 0, and the third one is 1. And this one is 1, and this one is 1, and this one is y3. So it means the probability of the 3rd class is y3, and the probability of the 1st class is y1. Probability of the 2nd class is y2. Okay, so this one is our likelihood, and we have to maximize this likelihood, but the likelihood is complicated, so we will take a log. So we can come up with the log likelihood, and then we want minimization problem. So we take a negative. So that's why we have negative log likelihood. So just take a log to this function and then take a negative. Then we have this one. It's a simple. Or if we take negative log to this one, then we have negative sign here, and then instead of a product we have a sum, and we take a log. Then we have a tk times log yk. Okay, this is cross entropy. Okay, when we have a lot of samples, when we have n samples, then we have to multiply all of them. Right, this one is still a likelihood function, and then we multiply all the samples because we assume that the samples are IID. Okay, for multi-class, then this one is the likelihood, and we have to multiply this likelihood for all the samples. And as we did in the previous slide, we take a log and we negate the log likelihood, so we have this one. So compared to this, the previous slide, we have this summation. And for multiple classes, we have summation here too. Okay, so now we have one objective function to minimize for neural networks. Again, this one is a label which is given, and this one is output of the neural network. So this one is actually function. yi is neural network, the output of neural network given xi. Okay, so then what should we do? So we have a neural network and we have objective function, and in the neural network we have all the parameters. Then what should we do? It's simple. Take a derivative and update. So for the gradient method, again, we're going to talk about this optimization method in the optimization chapter. Okay, so for now, let's assume that we need gradient of this loss function with respect to this parameter, and then we can train. So far, it's enough to say that, and we need this gradient. So now we're going to use the chain rule. That's why error looks like backward propagating based on this chain rule. So we will go through all these equations line by line. Okay, from the previous slide, we got these loss functions for a single sample. So when we have one sample, we can apply for the propagation to get the y. Okay, and then we have label t. Then this is our objective function. And we need this gradient, but we have a lot of layers. So first, we take a derivative with respect to y. So remember, we have a neural networks, and the output is y. And for binary class, we have only one output y, and we have input x. Y is the output of sigmoid functions. And right before this sigmoid function, we have a naught. So first, take a derivative with respect to y. You know how to take a derivative of this function with respect to y. Let's try this one. So when we take a derivative of this term with y, then it is minus t times 1 over y. And then how about this one? Minus 1 minus t times 1 over 1 minus y times minus 1. Then minus, and rearrange this term, then we get this one. Okay, now we want to take a derivative of this loss function with respect to a naught. A naught is right before this nonlinear function, before sigmoid. Okay, then instead of taking this derivative directly, then we're going to use the chain rule. So we apply this one first, and then we take a derivative of y with respect to a naught. So for your information, I put this equation here. So the derivative of sigmoid function with respect to the input is the sigmoid times 1 minus sigmoid. So this one will be sigmoid of a naught times 1 minus sigmoid a naught. And by the way, this sigmoid a naught is y, and this one is 1 minus y. And we multiply this term with this one, then we cancel these ones. So now we have y minus t. And you can do this by yourself too. The equations are not that complicated, but when you derive the equations, be careful with these subscripts and superscripts, okay? Okay, next, error backpropagation in detail. Okay, so first of all, we define the delta k and delta sub j to the power of L at the last layer and layer L. So this one is the delta at the last layer, this one is delta at the layer L, and this one is our definition. So we are going to use this notation for simplicity, okay? And delta k is the derivative of this loss function with respect to a sub k. So we calculate this one from the previous slide here. So we know how to calculate this one. And delta sub j to the power of L is defined by this term too, so at layer L. And for the last hidden unit, which means at L-1 layer, this one is right before this last layer, okay? And this one is a derivative of this loss function with respect to a sub j L, and we use a chain rule. So we take a derivative here, and then we have the same term here. So we take a derivative of b with respect to a. And this term is here, and the first term will be decomposed into this summation. So instead of calculating this derivative directly, then we calculate this derivative and multiply this derivative, and k, we will apply the summation through this k. We actually defined this one as delta k. You know, we don't have to replace this one with the delta k, but for convenience, we just use these notations, okay? This one is not derived notation. This one is our definition. We just use this notation, delta k. And look at this one. We take derivative of a sub k with respect to b sub h. A sub k is here. Okay, a sub k is the summation of b sub h. Then if we take a derivative of this term with this one, then only this term will survive. Then look at this term, partial derivative of bh with respect to a sub h. Then b sub h is actually a function of a sub h. So take a derivative is simply the derivative of this nonlinear function. For the other hidden units, it looks the same. We have a derivative of this nonlinear function and the delta and the weight. So the important thing is that this delta h dash is a multiplication of this term and this summation. Okay, so let's focus on this summation first. So in these summations, we have delta h L plus 1 times this weight. So we have delta here 1, delta 2, L plus 1, L plus 1, etc. And delta, let's say we have hn nodes in this layer. And this, to calculate this term, we have to calculate the weighted sum of all these deltas. So we have a weight. So that's what this summation does. And then we have to multiply this derivative of the nonlinear function. So in these derivations, it looks like delta k propagates in this direction from the last layer to the previous layer, and from the upper layer to the lower layer. So it looks like error is going back. So that's why we call it error back propagation, or backward propagation, or backprop, or sometimes bprop. Okay. This error back propagation is a result of the derivative. Okay, so when we calculate the derivative, we use the chain rule. Based on this chain rule, it looks like error is going back. Okay, so we have everything we need. Okay, so gradients are obtained for the layers, and for the last layer we need this one, and And this one can be rewritten by these two terms, and then this one is delta j and this one is b sub I. And for other layers, this one is decomposed into this derivative and this derivative, and this one is defined by this one, and this one is simply b sub I. And the first layer is the same as before, basically. So that's it. So what we need is the derivative of this loss function with respect to the parameters, and then we got this term for all the layers.